Hey, now that you understand the motor effect and the way in which magnetic fields can exert a torque on a current loop, let's dissect a real motor and see what's going on. I've got a couple of containers full of motors. The motors in this box, they look almost the same as the motors in this box. All right, well, they both have an axle that's going to spin. One thing I've noticed is all the motors that are encased in a full cylindrical case have a slightly different design than the ones that are flattened off cylinders. First of all, let's just show that these operate when connected to a power supply. I think 3 volts ought to be enough to make these go. Get my alligator clips. All right. Clip on there. How about this? I'll disconnect the battery so I can have them already clipped up. There we go. Okay. I don't know if you'll see it, but you definitely should hear it. Yeah, that baby's spinning. No matter when I connect and disconnect, this one seems to always start up. I got a suspicion that this other motor might not spin right when we connect it. I think this one might need a little flick of the wrist to get the axle going. Let's see if I'm right. All right. Connect it, nothing. Go watch, I'm gonna connect it and give it a kickstart, and then it goes. Disconnect, let's see if it goes when I connect it again. Nope, what about a kickstart? So what's the difference in the design of these two motors that makes this one require a kickstart and this one doesn't need it? All right, we gotta dig this apart, find out what's going on. Okay. Well, what we're going to find in any motor is the axle, of course, that it's mounted on, and then all of that blue wire, very thin gauge wire that's been wound several times, but that's the armature, that's the coil, that's the current loop that's receiving a torque. So how does the electrical current even get into this armature wire? So if we look back inside of the case here, where I make the connection, oop, that's not the piece I want, that's the piece. This is where the wire is connected, and you can probably see right in here are the brushes that make contact with the commutator. Now, does it show up on the video here? That's an insulating gap. So there's a certain point in time in which the coils wouldn't receive a torque at all, right? So if the brushes are contacting the commutator in its gaps, when it's in the position that it wouldn't receive any twist, that's perfect. It momentarily shuts off the motor. Because of its inertia, it spins a little more. The brushes now contact the metal part of the commutator just at the moment that the alignment of the armature would be such that it wants to get a torque, and then it just keeps on spinning, spinning, spinning. So this is what's happening. Every time I disconnect, this motor always falls into the position where it doesn't receive a torque and the brushes are in the gaps. So as long as I give it a little flick, I can reestablish contact at the commutator and it keeps on moving. If I take this one apart, what we'll find is instead of just 2 gaps in the commutator, it has 3 gaps that lead to 3 separate armatures. Actually, I have another version of this design that I'll show you in another video.